Welcome again. In this presentation, I will discuss how to avoid set point kicks with 2DOF PID. We will discuss what is meant by set point, proportional and derivative kicks are. We will show how to split a controller in IPD form. We will also verify offset free tracking condition for this form. The standard PID control law has a shortcoming. If there is a sudden change in the set point, say in the form of a step change, both proportional and derivative modes will introduce large jumps in the control effort known as set point kick. The large change produced by proportional mode is known as proportional kick. The derivative mode could produce even larger change. It could be the derivative of a step change. This is known as the derivative kick. Both derivative and proportional kicks are generally not acceptable. We solve this in a feedback form given in the next slide. Consider a PID control law with a filtered derivative action. Filtering comes through this denominator term. Write E as R minus Y. When I substitute, I get this expression. To remove the set point kick, we propose the following form. What we have done is, we have dropped a few terms. For example, the reference signal or the set point signal does not come in this at all. The second term has proportional mode and derivative mode. These are the two modes that create kicks. So the reference signal is not even included here, it is dropped from here, and the error signal is sent through a derivative mode. Because of this, we say that the set point kick has been removed, but we will explain the structure shortly. This is the control law from the previous slide. You will have to remember this. You may even want to write this down. We will need this later in this video. Let us group the terms involving R here and Y here. You can see that Y has proportional and derivative terms plus the integral term that comes from here. Why does the integral term have an extra element here, this 1 plus tau ds by n? We will explain this shortly. So we have grouped all the terms that multiply R, and here all the terms that multiply Y are inside these square brackets. We can simplify this. There is not much change here. Here we have multiplied tau is into this because the denominator of the second term is already present. We can verify this. This is of the form U equals Tc by Rc into R minus Sc by Rc into Y, the standard 2DOF form. So this is Tc, this is Rc, and similarly you can get Sc here and Rc is the same. It is easy for you to verify. Tc equals Sc of S equals 0. Remember, we are still working with Laplace transform here. We are yet to discretize it yet, which we will do shortly. But for offset free tracking, here is the condition to be used. It is equal to K. That is easy to verify. Tc you can see to be K. Similarly, you evaluate Sc from here and substitute S equals 0, you get K. So the offset free tracking condition is satisfied. Let me summarize the offset free tracking condition of a step input. This is in discrete time mode. For continuous time systems you get this expression, and it is in fact the second condition that we have invoked in the previous slide. If this is satisfied and if you have integral mode, then steps will not produce any offset. So let us start with that expression that we had a couple of slides ago, and this can be implemented as the following. Here is the schematic of this. Notice that the second term that involves only y is implemented through the feedback term. Y comes here, it goes through the proportional and derivative mode, and you have a minus sign here, that is that minus sign. So u equals the first term is given here, what you have in front of r minus y is inside this box, and then r minus y comes here, this is r minus y multiplied by this box, it gives you this first term and that comes here. The second term is this whatever is inside this box multiplied by y, which is the second term, that is u. So this schematic indeed implements this control law. In fact, that is the way one would go about implementing such control laws. This is known as IPD form, I-PD form, I-PD controller, where the first term denotes what goes through forward path. So only the integral goes through the forward path and the PD goes through the backward path. So unless I have 1 plus tau ds by n here also, because this is the denominator here, the same denominator is present here, unless both are identical I cannot keep RC the same. We got RC the same from these two terms. That is possible only if I have this term. That is the reason for including this extra term in the integral form. Now let us look at the discrete equivalent using backward difference rule. Here is the control law where the expressions for RC, TC, SC are given below and the meaning of S0, S1, S2 all small s are given here. I would encourage you to derive these terms. Some of these are explained in the textbook. You can also show the offset free tracking condition in the discrete form, namely SCF1. If you substitute 1 here, it will be S0 plus S1 plus S2, and you can show that it is equal to TC, which is this. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.